PhD defense of Maarek. We are a very large committee here, and I'm happy to join Paul Schneider. I've been nominated to preside with the president of the committee. Peter Botte on my left. We also have in the committee Professor Greta Trygvason, Professor Stéphane Vincent, and Professor Pascal Gardin, and the supervisor Stéphane Coquinet and Stéphane Zalewski. And so Jakob, you will have about 45 minutes to present your work, and then we will start the questions. Okay.
Okay, well, thank you all the jury for being here. Thank you everyone for came to my PhD defense. Today I'll be presenting on the work I've done in the past few years on a thesis entitled Mass Transfer at Fluid Interfaces at Large Péclet Numbers. So mass transfer in multiphase flows occurs in many different industrial processes and natural processes. Here we show two examples. On the left, we have a bubble column reactor, which is used to promote mixing of gases and liquids. Can be used for applications such as carbon capture. On the right, we have a top view of a metallurgical ladle, where you have a liquid steel with a top layer of slag, with gas being injected from the bottom. And this is used to promote mixing of the steel and promote the refining of steel. So these type of problems are very challenging. First of all, it's a coupled multiphysics problem with many different non-dimensional parameters. So it becomes nearly impossible to have a scaled model that achieves similarity in all different parameters. So that you are left with either using the industrial size experiment, or you have to perform some numerical simulations. So numerical simulations have their own challenges due to the vast range of length scales involved in such problems. So here we show an example of, let's say, a bubble with an AMR mesh. Then what we can see is as the grid size gets refined, you have the cell count goes up with, in this case, you have a scaling of around the grid size squared, indicating refining around a surface. And you can also compare the speed for the amount of CPU hours for a fixed amount of time, the simulation time, which will scale more with x cubed in this case for this simulation, indicating that you also have a restriction of the time step, which is making the computation of such a simulation more expensive and becomes infeasible for very, very small length scales. So we can take an example of the bubble column reactor, where you consider at the reactor scale, you can have a length scale of meters, which includes sworn patterns, collective breakup and coalescence. It can include stratification. At smaller scales, you have the bubble scale, which is on the size of millimeters. And that includes, let's say, individual bubble interactions. At this even smaller scale, you have the momentum boundary layer around each bubble, which will scale with the approximately the diameter of the bubble divided by the square roots of the Reynolds. So this brings us down from 1 meter to 100 microns. And lastly, you have the concentration boundary layer of a diffusive species, which will scale as approximately the square root of the Péclet, which is also the Reynolds times the Schmidt. And this brings us from 1 meter all the way down to 5 microns. So just in general, we can say that the upper limit of computational feasibility using high-performance computing, using adaptive mesh refinement, at this day and time is still around 4 orders of magnitude maximum. So going from the top all the way to the bottom is not possible. So, well, an advantage, something we can do instead is we can say that the very small scales, by knowing understanding of how what terms are dominant, we can develop a model that represents what the profile of the concentration boundary layer looks like at a small scale. So this is very similar to what's done in single phase turbulence modeling, where they use wall functions to represent the viscous sublayer and accurately capture the shear stress near a wall, while keeping the grid size of the what's required to resolve in the bulk. So you can say we're doing wall functions for the species transport equation. The end goal is to be able to perform mass transfer simulations of industrial processes at a reasonable cost. So reasonable is a bit vague, and how we will define it as is the cost of approximately the same order as the cost of the numerical simulation of a DNS. So in this presentation, we will start off with a bit of theoretical modeling, explaining the governing equations, some boundary layer theory, moving on to numerical modeling of how we take these equations, solve them on a grid, and go on to how we perform subgrid modeling in the developed framework. Then we'll apply this as a validation case to species transfer in single rising bubbles. And finally, we will move to a quasi-industrial process, which is a model substitute of a metallurgical ladle. And we'll end with some conclusions. So we can consider the governing equations of the incompressible Navier-Stokes equations for a fluid in each phase separately. So you have this is the single phase Navier-Stokes equations of incompressible. So you have the divergence-free condition. And you can consider the boundary conditions at the interface to be given by the Young-Laplace law, which relates the curvature to the pressure jump, assuming constant surface tension, and the shear stress continuity at the interface. Next, you can consider the scalar transport equation in fluid A, where we've written here the advection diffusion equation, with the second term being the divergence of the diffusive flux. And we will be considering Fickian diffusion such that the diffusive flux can be written as a product of the gradient of the concentration field multiplied by the molecular diffusivity. Now you can consider the interfacial flux, where we consider here the general form, where the first term represents a convective flux due to the change in the position of the interface with respect to the both fluids, and the second term being the diffusive flux across the interface. In the case where we consider a dilute species transfer, which means that there is no volume change between phases, this first term is 0, and so we can write the first equilibrium condition at the interface to be related to the diffusivity of fluid A multiplied by the concentration, the normal derivative of the concentration field at the interface of fluid A is equal to the same likewise for fluid B. Lastly, we consider a jump in the concentration field at the interface given by Henry's law, which relates for a gas-liquid system. It relates the partial pressure in the gas phase to the dissolved concentration in the liquid phase. In general, the constant P is at least a function of pressure and temperature, but for these simulations we will be considering it constant. Now moving more towards some boundary layer theory. So we take in the limit that the Schmidt number is much greater than 1. This means that we can write that the concentration boundary layer is much smaller than the viscous boundary layer, is much smaller than a R, which represents the radius of curvature of local topological structures. We consider that fluid A controls transfer such that you can write that the concentration in fluid B is near constant, which gives a Dirichlet condition at the interface. And now we achieve a form of the general form of a boundary layer equation where we consider a slip velocity, a shear rate, and the normal concentration at the and being advected tangentially, and diffusion happened normally to the interface with applied boundary conditions where you have in the far field you have a certain condition, and then at the interface you have the concentration at the interface. We can consider the two limiting cases where if omega is equal to 0, that would correspond to a free surface, and if the slip velocity is equal to 0, that would correspond to a rigid surface. So this problem in its general form has been solved by a change of variables by Appelblatt, and the actual form of both the concentration field and the gradient at the interface is a bit nasty. It's an improper integral of Bessel functions, but instead here we plot on the right, we plot the general form of the concentration gradient at the interface with respect to a non-dimensional distance x. So you can see as x approaches 1, you shift from a 1/2 scaling to a 1/3 scaling, and then on the bottom here we plot essentially the slope of the function, showing that the intermediate range scales over approximately 3 decades. And this is a pretty large range, and will become important in the end when we will see that the final problem we're discussing is in this intermediate range. We can write the mass transfer coefficient as the gradient of this non-dimensional gradient evaluated at x, multiplied by the diffusivity times the shear rate over the slip velocity. Now we can consider in the two cases of the two limiting cases, where for a free surface you have a problem equivalent to a transient diffusion problem, where the time is replaced by a distance, and gives the classic function of the complementary error function with a mass transfer coefficient that scales with the Schmidt number squared and the Sherwood number to the 1/2 and the Schmidt number squared. The Sherwood number is the Schmidt number squared. The rigid surface is the problem known in the literature as the Levesque problem, which gives a concentration field that has this. It's actually the integral is relatively similar to the error function, except for that you have a cubed instead of a squared. And then the mass transfer coefficient will scale with this diffusivity to the 2/3, and you can write the Sherwood number will scale with a friction Reynolds number to the 2/3 and the Schmidt number to the 1/3, recovering what we had seen before. So now we can go to numerical modeling, where we take these governing equations and apply them discretely. The tool we use is the Basilisk flow solver developed by Stéphane Papinet and collaborators. It's a free software PDE solver on Cartesian grids, and uses a tree-based spatial characterization with adaptive mesh refinement to consider local variations of scales. The transport equations are solved with the finite volume method, which has good conservation properties. And this user base has grown large in the past few years, which is pretty exciting. And so we can consider, going back to the original problem, of what are the different length scales resolved. So for a quad tree grid, you can consider the size of the largest cell of L. And then you can consider the smallest grid size is going to be the number of levels in the tree, and then you're going to have 2 times the smallest grid size is equal to the total grid size divided by 2 times the max level. To solve the incompressible Navier-Stokes equations, we are using the multiphase incompressible Navier-Stokes equations. We are using the one-fluid method, where you replace the interface jump conditions with a change in material properties, and replace the surface tension term, or approximate the surface tension term with a Dirac delta function. The indicator, we use an indicator to describe the relative position of the phases, which is 1 in one phase and 0 in the other phase, and it can be approximated numerically as with the volume fraction given by the integral over the control volume of the Heaviside function. Then we can write that the material properties will have some sort of weighted average of this volume fraction to approximate the surface tension term. We're using the continuum surface force method with height functions which reduce spurious currents. And the pressure velocity coupling is achieved with the projection method. To transport the interface, we introduce a new PDE, which considers the transport of the volume fraction, where we can reconstruct the interface. For each, we can look at, on the right, you can see the data structure, which represents in each cell how much of one phase versus the other phase takes up the cell. And then you can reconstruct the interface with a piecewise linear planar reconstruction in each interfacial cell. To transport the volume fraction from one cell to the adjacent cell, we use the geometric volume of fluid method, which geometrically recomputes this integral of the Heaviside function in the advected, the fluxed region. So to tackle the problem at the end, which is a three-phase problem, we had to investigate a little bit of modeling three-phase flows. So instead of having one volume fraction field that considers one phase explicitly and the second phase implicitly, we track all three phases individually and enforce that the volume fractions add to one. The surface tension term is now replaced by a three-phase CSF model, which considers a phasic curvature and a phasic surface tension field, surface tension coefficient that creates a net force in each interfacial cell that is equivalent to the surface tension between two individual phases. And lastly, we did some initial validation with a liquid lens in a double droplet morphology, and using the height function curvature everywhere was creating erroneous results. So we modified the calculation of curvature at the triple point using a smooth volume fraction and taking a gradient of this smooth volume fraction field to compute first the normal and then the curvature, which led to better results. So now we can move more towards the main part of this thesis, which is solving the resolution of the scalar transport equation. So two approaches are known in the literature. The first approach is a one-fluid method similar to what we've just seen, where one transport equation is solved with the jump conditions embedded algebraically into the transport equation. The advantages of this method is that it's more efficient in that you're resolving only one PDE. And you can have a time implicit discretization, which is allows for larger time steps. A basilisk implementation that's a somewhat of a hybrid implementation was done just when I was starting my PhD, and we adapted this implementation for three phases as part of my work. The second approach is the two-fluid method, where the transport equation is solved separately in each phase. Henry's law is applied only at the interface, and the advantages are that it's more spatially accurate, and the fact that each term, the interfacial transfer term is computed explicitly, allows for a subgrid modeling approach. So we can consider the two-fluid method, and we can consider the data structure that's stored in each cell, which is the species amount in each phase. So you have two tracked variables, G1 and G2, which are given by the concentration in that phase multiplied by the volume fraction. And then you can advect these tracer fields consistently with the volume of fluid advection that prevents diffusive transport across the interface during the advection step. And lastly, we're going to consider the phasic diffusion equation with coupled source terms. So you can write on the bottom, you considered the phasic diffusion equation, where we've considered an effective diffusivity and a source term R. So you can see the source terms are equal and opposite. And the effective diffusivity is computed by the molecular diffusivity the phasic face area, and this term gamma, which is we're going to consider a correction term, and can be considered either in a resolved case a property of the geometry, or in a case of a subgridding modeling case is going to be how we introduce the subgrid correction. We can consider the two-fluid method with the transmission coupling at the interface. So the gradient is approximated from the controlling phase. We can write the source term as the diffusivity multiplied by a new subgrid, new correction term, the interfacial area in the cell, multiplied by the normal derivative of the concentration field. And theoretically, both of these are equal, but in terms of a numerical approximation, it makes sense to take the side that is more resistive. So we would extrapolate the concentration field from one side, use Henry's law to relate the concentration at the interface, and then compute the concentration derivative on the more resistive side. So we can consider a validation of our two-fluid method, where we considered a sphere moving in a uniform field with initial concentration of 1 inside the sphere and 0 outside the sphere. There is a diffusivity ratio of 10 and a partition coefficient of 10 to the negative 3. So on the right, you can see the total mass transfer as a function of time, where we consider the two approaches. So in the dashed lines, you have the one-fluid approach, and in the solid lines, you have the two-fluid approach. And you can see that the two-fluid approach converges to the expected result quicker. But that doesn't necessarily mean it's more efficient, because using an explicit coupling requires that you satisfy, let's say, you satisfy time-step restrictions, as opposed to using a time-implicit characterization for the diffusion term with the one-fluid method. So now we can consider a subgrid approach. So you can see here on the right approximately what we're trying to do. So you have a concentration, you have on the y-axis, you have, let's say, the interface. In the gray, you represent essentially the concentration in the first interfacial cell and the second interfacial cell. You can use a piecewise linear reconstruction to compute the gradient, like was done in standard schemes. And then you have in blue, you have the profile that we assume a priori, and you can compute the gradient of this profile on XF. And this would represent a subgrid representation of the gradient. So two approaches for the subgrid model exist in the literature. So the first approach was done by Professor Fredrickson and considers is compatible with the front tracking approach. In this approach, you track the data structure is essentially attached to each marker and represents the amount of concentration inside a fixed distance from the interface. And the second approach is the geometric volume-of-fluid approach performed by André Weiner and Dieter Bothe. And this considers the exact same data structure we had before, where you're tracking the amount of the species amount in each phase. Likewise, the difference comes from the treatment of the convective term. So in the marker-based approach, the convective term is treated by a combination of the Lagrangian movement of the marker points and then a computation of the local strain rate on the surface. Whereas in the geometric volume of fluid approach, as we will see, we compute basically the same approach of the volume of fluid geometric fluxing, but instead of having a heaviside function, we will be using a boundary layer profile. So on the left, you can consider a bubble with a coarse grid. And we have to, in a single interfacial cell, we have to assume the profile of the boundary layer. So for taking a free surface approximation, you can assume it to have an error function profile. And we can describe this then mathematically as the concentration distribution in an interfacial cell will be given by the distance from the interface multiplied by the error function of the distance of the interface scaled by the boundary conditions at the interface in the far field. You can write our our tracked variable g as the average of this concentration field in the cell, or is given by the integral over the cut cell. And then the boundary layer thickness is defined implicitly as a function of g and the geometry and boundary conditions. So this allows us to use a Newton's-like method to compute the boundary layer thickness locally in each cell. The normal derivative in the phase is given by the derivative of the error function, and would be 0 outside of the phase. And then we can consider going back to correcting each term in the scalar transport equation. So the convective flux will be given by, instead of integrating the Heaviside function, we'll now be integrating this concentration boundary layer profile. The diffusive flux will be considering the projection of the normal gradient on the cell face, and taking the surface integral on the cell face. And then we can go back to computing this effective diffusivity, where we have replaced these correction terms gamma with a ratio between the subgrid-scale concentration gradient and the scheme we were using before. A similar thing is done for the concentration, the correction term at the interface, where you're taking the gradient by the subgrid approximation and the approach we were using before, and we use this to scale the source term. Lastly, we decided to try to generalize our approach to other profiles. And this is basically because performing the volume integrals is not necessarily easy to implement, and in some cases won't exist. So we can approximate a single function by a shallow neural network given by essentially a linear combination of the same term we had before, and then you've added just this constant term inside the error function, and we derived the closed form integral expressions of this new boundary layer profile that we can use to approximate more general terms profiles. So with this approach, we were able to fit the Levesque profile that we'd seen before, and due to the way we trained the neural network, we were able to successfully learn the asymptotic behavior of the function, the derivative, which was a nice property up to machine precision. So now we're going to take this framework we've developed, apply it on the case of single rising bubbles. So we can see here on the right approximately what our simulation would look like. On the left-hand side, you have a bubble advancing. You have the concentration field on the left-hand side, and you have the rise velocity on the right-hand side. So we're going to be solving these equations in 3 dimensions. And we assume that the gas concentration is constant. The Schmidt number we can vary from an order of 100 up to something much larger than what we would see physically of 10 to the 8. And we performed a wide variety of test cases from Stokes flow regime up until a Reynolds number of up to around 700, which would correspond to a air bubble of approximately 2 millimeters in diameter in water. These bubbles can undergo deformation, and in certain cases we will see the boundary layer separation in the wake due to a trailing vortex. And we can compute, to compare the results, we'd be using local quantities of the local Sherwood number, which is essentially a scaled concentration gradient at the interface. And the tangential velocity, in the case of the Stokes flow regime, we can compare directly with theory. And in the case of the more inertial regimes with deformation, we will be compared to refined 2D simulations. So in the Stokes flow regime, we can consider a spherical bubble in the Stokes flow regime. This flow profile is known as from the Hadamard-Rajimsky equation. And so we can compute directly we did our 3D simulations, and we can compare directly the interface tangent velocity with the expected solution. and we see good agreement. And so then we compare our 3D subgrid scale model with a resolved axisymmetric model for a fixed Schmidt number of, and we can see that the resolved axisymmetric will approach the correct profile as the grid is refined, whereas the subgrid model always well approximates the expected profile. This expected profile for a finite Schmidt number can be solved from a pseudo-analytic solution in the literature, where you integrate numerically a parabolized advection diffusion equation. And in the limit that the Péclet number approaches infinity, an analytic solution exists. So we can see now that was for a fixed Schmidt number, but now we can consider our subgrid scale model varying the Schmidt number from the order of 100 up to 10 to the 8. And we can see the points are our subgrid model. The curve is the reference solution. And we can see a good agreement. And we can see as the Schmidt number increases, we approach the analytic solution. So now we can move on to an inertial regime under different cases. On the left, you have an ellipsoidal bubble without a trailing wake. In the middle, you have an ellipsoidal bubble with a trailing wake. And you can see that the boundary layer separation occurs at the position of the vortex. And on the right, you have a dimpled bubble with the trailing wake. On the left-hand side of each panel is the resolved axisymmetric simulations, which is 40 times refined compared to the right of the subgrid scale model in 3D. And qualitatively, we can see very good agreement between the two axisymmetric and 3D simulations. We can consider in the case that was in the middle, we can see how the concentration field would vary. So you can see at low Schmidt numbers, you have a much more, the concentration field is much higher. But you can see at the same point, the same boundary layer separation, you will have, you can see where the wake is separated in all cases. And in the case of, on the right-hand side, we can consider what is the boundary layer thickness compared to the grid size at the maximum point, where the boundary layer thickness is the thinnest. And in this case, it would correspond to the boundary layer thickness being around 70 times smaller than the grid size. So what we would like to then do is compare qualitatively what our new local Sherwood number would look like as a function of the polar angle. So on the left-hand side, you see the tangent velocity comparing the 3D and the axisymmetric simulations. And on the right-hand side, you can see our spatially averaged local Sherwood number. And we see a very good agreement, which is nice to see. And finally, we can consider, for the 3D subgrid case, we can vary the Schmidt number as a function and compute the local Sherwood number. And so what you can see is, before the boundary layer separates, you have a collapse onto a single curve with respect to a normalized of the square root of the Péclet number. And in the gray points, we have plotted a reference numerical simulation. And unfortunately, you can see that the position of the boundary layer separation is slightly different, and that in the before the boundary layer, we are actually under predicting compared to this reference simulation. But this reference simulation was done with a different, done with an arbitrary Lagrangian Eulerian code. And we would hypothesize that the difference is not from an approximation of the subgrid model, but rather due to a difference in the local velocity field. But this indicates one of the challenges of this type of approach is that first, to come up with a local Sherwood number, you need to have a multiphase flow solver, and then you need to have a subgrid model that works, and then you can try to directly compare, which there are not that many that exist. And then you have to not only consider the effectiveness of the subgrid model, but you have to consider how the flow is being resolved as well. So these past results were for a statistically a stationary, a steady state regime. And we can consider instead the Sherwood number in the transient regime. And this is even more challenging than doing the steady state regime, because as you can see, as the boundary layer thickness is growing, you would have a much higher local Sherwood number than you could possibly resolve numerically. And so the only way we can directly compare is using a grid conversion study of our subgrid model. So here on the right, we have plotted the global Sherwood number as a function of a non-dimensional time. And we can see that as for different Schmidt numbers and different grid resolutions, we can see a relatively good collapse of all the different simulations performed. A similar analysis can be done for the local Sherwood number and is done in my thesis. So lastly, we can consider a path instability. So the case we've considered is from the standard basilisk test cases, and corresponds to a ellipsoidal bubble undergoing a zigzag path instability. So in our simulation, we have verified that the Reynolds number is approximately what was reported in the literature. And we can then investigate qualitatively what we see occurring. So we can see on the left-hand side, we're plotting the translational Reynolds number as a function of time, and then in the blue curve you're plotting the Reynolds number, and in the red curve you're plotting the global Sherwood number. And we can see that as the Reynolds number hits 0, which corresponds to the bubble changing direction, you see a locally reduced Sherwood number, which would correspond to the point at which the boundary layer is separating and injecting species into the fluid. And then as a case where it didn't work very well, we can consider a viscous drop, which we've approximated with our Levesque profile to have the boundary layer profile for a rigid surface. And we can see that as we try to compare to a reference solution, we don't have a good agreement between our subgrid model and the reference, the pseudo-analytic solution. But we can compare to the interface tangent velocity, and we can see that the error is coming from the interface tangent velocity and not from our subgrid model. So this is work for the future to try to understand why this case didn't work as well as the free surface bubble cases. So now we'll be moving from these more, let's say, simple cases of a single rising bubble and moving towards a model in industrial process. So we can consider the problem of a secondary metallurgy refining ladle, where you have liquid steel and slag, and you're trying to promote the desulfurization of steel with the global kinetics being governed by the convective transport in steel. So we can consider the Schmidt number of the liquid metal to be of the order of 10,000. The Reynolds number is of the order of 1,000,000, and the partition coefficient, which compares the solubility in the slag to the steel, to be measured to be around 350. And this system, the transport is governed by the transport, the diffusive transport in the steel phase. So this problem working with the liquid metal is challenging, and so we've worked off of a thesis that was my predecessor, Nelson Joubert. So we consider a oil, water, and air experiment where you have air being injected from the bottom at a fixed flow rate, and then you have a thin oil layer on top that gets perturbed by the rising bubble plume, And you can see here on the left-hand side 2 videos of at a low flow rate and at a high flow rate. At a low flow rate, the perturbations of the oil film are relatively small, and then at a high flow rate, you have a continuous fragmentation of the oil layer. So we can see what is measured in these experiments. Well, the first measure, that's a measure of, let's say, the hydrodynamics, is from looking at the top. You see what is the size of the water or liquid metal being pushed into the top layer. So this can be measured visually, which is why it's used. And then on the right, you can see, let's say this is referred to as the open eye. And on the right, you can see the open eye area as a function of flow rate. So I would like to focus first on also you can see 2 cases where an additive was added to one of the 2 liquids, where thymol was added to the liquid, to the water phase, and colorant was added to the oil phase. So we would expect that this would change the surface tension coefficient, which seems to have an effect on the open eye area, which lets us believe that capillary effects are important. Then to measure mass transfer, they consider essentially a 1D model that you measure the concentration in the water phase and assume that the resistivity in the oil phase is small. And from the concentration field as a function of time, you can extrapolate the mass transfer coefficient at the interface. So this is not the first experiment. There was I would say around the order of between 5 to 10 experiments in the literature, and one of them also being done by Stéphane Vincent before Nelson Joubert, with Leonardo Dijon de Campos. And so you can consider the open eye size area as a function of a modified Froude number, comparing inertia to gravity. And generally, models have shown that a good approximation is that this modified Froude number, that the open eye area is approximately linear with this modified Froude number. And then you can consider this global Sherwood number, which is basically taking the mass transfer coefficient multiplied by the exchange area, and then normalizing by the size of the tank, the diffusivity in the water phase, and the height of the the water layer. And you can see essentially a scattering of the different experiments. And you can see that there's essentially 2 regimes that corresponds to the critical point corresponds to the fragmentation of the oil layer, which would greatly increase the exchange area. But in just focusing on the first regime, you can still see that the power law scaling of the Sherwood number with respect to the Schmidt number, with respect to the Froude number, is still changes between different experiments. So this is an outstanding question, and something we try to answer a little bit with this work. So our experiment is the one in the blue curve, and you can see we're focusing on the first regime, where we see a very weak sensitivity of the Sherwood number, of the Froude number to the Sherwood number. So we consider 6 flow rates that were in the same range as was done in the physical experiment, and corresponds to a similarity of the Froude number with respect to the industrial ladle. We first start the hydrodynamics to remove the transient state of the simulation to save time before we start mass transfer. And for the first time, using our developed subgrid modeling scheme, we can simulate Schmidt numbers that are high, of the order of 1480, which is the physical value, with the partition coefficient at the interface. And to compare with previously performed results by Nelson Joubert, we also consider lower Schmidt numbers for a single case. And lastly, we tested a grid convergence of 2 different levels to see that the results don't change much between refinement. So you can see here what our numerical simulations would look like. So again, at a lower flow rate, you have a relatively small deformation of the oil layer. And then on the right, you can see a continuous fragmentation of the oil film. So we can perform a similar measurement of the open eye, where we look from the top and measure the size of the open eye as a function of time. But what we notice by taking a cross-section of the oil film is that we have a very thin film of oil forming at the top, which would actually cover from what the opaque image you're seeing at the top. And this was observed to be grid dependent. So to try to compare simulations between different grid sizes directly, we would actually just remove this thin film in post-processing, and we report the results at a single grid size with the oil film and without the oil film. And you can see that we're within the expected range of the physical experiment, but without the oil film corresponds better to the measured results. So lastly, we can then consider, we've developed a phenomenological model for the open eye as a function of the given flow rate. And we've considered essentially 4 phenomena, where you have the bubble plume, you have the bubble plume impacting the free surface and being pushed radially outwards, creating a radial jet. And then you have a stress balance on the oil film, on the water oil film, the water interface of the oil film. And lastly, to consider this thin film, we've used a viscous capillary stress balance on to come up with a meniscus length. So these individual, with a simulation, we can directly measure these different phenomena independently, and we can then fit coefficients of our expected scaling from the data and compare directly to literature. And we were able to see a relative agreement with the experimental data. Lastly, we can consider the results for the global Sherwood number, where on the right we have plotted, let's say, the transient global Sherwood number as a function of time. We wait up until a point where it reaches an approximately steady state, and then average that over about 1 second to come up with the global Sherwood number and compare to the experiment. And for the simulations done in the first regime, we were able to see good agreement for the first time, which was very, very exciting. So now that we've matched the global Sherwood number, we can try to investigate what's happening locally. So on the left, you can see essentially the local Sherwood number spatially distributed in the ladle. And you can see that there is a thin annulus surrounding the open eye size, where the Sherwood number is very high. And away from this annulus, the Sherwood number is low. And this is natural, as you would expect, essentially the shear of the bubble plume to create essentially a forced convection region on this annulus. And so one thing that was, we can measure what the Sherwood number would be locally and compared to our grid size. And we can see that the boundary layer thickness compared to the lower, coarser grid is approximately 10 times smaller. So we would require much more computational power to resolve this numerically. And lastly, we can measure the local Sherwood number with respect to the distance from the open eye. And we can see that the Sherwood number appears to be weakly sensitive to the distance from to the flow rate, which is unintuitive. So to try to investigate further, we can also measure the local flow properties near the open eye. So we've measured the slip velocity at the open eye, in the annulus next to the open eye, and the shear rate. And we can see that both of these are also appear to be weakly sensitive to the flow rate. From these direct measures, we can recall our boundary layer model. We can compute this non-dimensional distance x by assuming the distance, by measuring the distance of the width of the annulus, the shear rate, the slip velocity, and our known Schmidt number. And we can see that approximately our Schmidt number, where you'd expect the transition from the 1/2 to the 1/3, would occur between around 100. So between the Schmidt number of 1480, we're within this intermediate range of 3 decades, where you can see if we take now our Schmidt number of 1, the Schmidt number of 1,000, and extrapolate, let's say, using this model of essentially comparing the ratio of the local of the fixed Schmidt number to the critical Schmidt number. You can extrapolate through our data points, and comparing to the 1/2 and 1/3 scaling, we see that we are in an intermediate range. Lastly, we can directly measure the local Sherwood number in the annulus using our measured non-dimensional distance. And we can use this estimate to compare it with what we saw numerically for the local Schmidt number, and we see a relatively good agreement. So to develop a model for the global Schmidt number, the global Sherwood number, we can assume that mass transfer only occurs in the annulus, and then assuming that the open eye area is linear with the modified Froude number. So the radius of the open eye would then be to the 1/2 of the modified Froude number. We can basically take an approximation of the thickness of the width of the annulus multiplied by the circumference of the annulus, taking then our local Sherwood number in the annulus, which we will assume to be constant, and divide by the size of the tank. And this would give a Sherwood number of a global Sherwood number to be approximately n to the 1/2, which is weakly sensitive, but not exactly what we were seeing experimentally and numerically. But this seems to be correspond relatively well what we saw in this one experiment, but it wasn't what we were seeing in the other experiments. So an outstanding question, and something we're trying to answer right now, is that we're simulating the other experiments, or one other experiment, and trying to see if we can recover the same trend and then diagnose what changes between the two different experiments. So as conclusions, we can say that we've developed and validated a 2-fluid method for dilute species transfer, and then added a subgrid-scale modeling framework on top of this 2-fluid method with the 2-fluid geometric VOF approach. We can say our model is sensitive to the local velocity field, and so therefore we can say that the numerical methods to resolve the Navier-Stokes would likely be important in computing the overall mass transfer. And the validation of this subgrid-scale model is challenging, requiring that you have a multiphase flow solver, a subgrid-scale model, and you would have to be able to compare solvers. We need to have a way of being able to compare the success of different solvers in the literature. Lastly, we've taken our model, our subgrid-scale model, and studied a quasi-industrial process with realistic Schmidt numbers, and we had agreement with the experimental measurements for the first time. An advantage of performing CFD simulations is that we can have a rich data set to draw from or to investigate, and allow us to investigate local dynamics and understand how the local dynamics affect what we observe globally. Going forward, well, we would like to try to combine the subgrid-scale modeling of the scalar transport equation with the subgrid-scale model of the multiphase Navier-Stokes equations, so that you can even reduce the computational cost of these simulations even further. We would like to expand our framework to include reactions and volume changes such that you can simulate important industrial processes. And then we would like to use the framework to characterize different processes. Thank you all for your attention, and I'll be happy to take any questions.